Okay, it's already a little after 10, so we'll begin now, right? Hopefully other people will join, but the meeting is being recorded at this point in time. So they could always look at the video if they don't come in, right? So we continuing from the last day, right? Okay, so this was where we stopped, right? We're looking at the theorem here, L of yt is ys. So we want the Laplace of the Heaviside by a function, right? So h at t minus t naught, y at t minus t naught is equal to e to the minus s t naught by y of s, right? Equivalently, this could be, this theorem here could be written in this form here underneath, right? Which is just basically, you take the L inverse here and L inverse here. So the Laplace operator, the Laplace inverse will cancel the Laplace here, and you'll get the Laplace inverse on the right-hand side, which is this form underneath here, right? So I promise you to look at the proof of this theorem, right? So let's look at the proof of this theorem here, right? Okay, so L of h of t minus t naught, y t minus t naught is equal to e to the minus s t naught by y of s. So basically, we apply the definition. So by definition, the Laplace of h of t minus t naught, y of t minus t naught is the integral between infinity and 0, e of e to the minus st by this stuff here in the brackets on the left-hand side, h at t minus t naught, y at t minus t naught. Right. Now remember that the Heaviside function t minus t naught is defined to be 0 for less than t naught, and it's defined to be 1 for anything t naught and greater, right? So which means we could break up this here, because this is a piecewise function. We could break up the Heaviside function t minus t naught into the part with 0, which is the limits here will be t naught and 0, right? And between infinity and t naught, the function will be defined to be 1. So you have to multiply 0 by y at t minus t naught, e to the minus st. And on this side here, between infinity and t naught, you multiply e to the minus st by 1 by y at t minus t naught. So of course, this part here on the left here, because you're multiplying by 0, this part will drop off. So you'll only get this part here on the right-hand side, right? So this is the only part here that will survive. So this is the integral you really have to find, right? Now, this function here, y of t minus t naught, right? In its current form, right? It's kind of messy to find the integral of this here. It might be a bit confusing, right? So what you do here, you change, you make a what you call a change of variable, right? So you let this part here, t minus t naught, be a variable. So in this case here, we call it t, capital T, right? So sometime in different texts, they might call it gamma or tau, something like that. It doesn't matter what variable you use. In this case here, I'm using capital T, so let capital T be T, let capital T equal to T minus T naught, right? So of course, if you're differentiating capital T here, because you want to change this part here, the dt, to d capital T. So if you're differentiating the t here, then you have to also differentiate the right-hand side. But you remember this t naught here is a constant. So when you differentiate a constant, you'll get 0, of course. So d capital T is d of common t, because the t naught will drop out, because that is a constant, right? Now, if you rearrange this equation here, you'll get t is equal to capital T plus t naught. Because what you want to do, you want to make a substitution for this little t on top here, right? And when, remember the limits now, you have to look at the limits in terms of your new variable, which is capital T. Remember this, these limits here for common t, right? So we have to see the connection between capital T and common t. So when t is t naught, right, that is the lower limit, what you have here, you'll have capital T is t naught minus t naught, which is 0. So capital T is 0. So therefore, this bottom limit here, when you're dealing in a new variable, becomes 0. Right? The upper limit, of course, capital T when common T is infinity, well, infinity minus a constant is infinity. So the upper limit remains the same. Right? So now we could change, right? So we have the minus s, your common t is t plus t naught, and your t minus t naught, y of t minus t naught is y of capital T here now. And your dt, d common t is d capital T. So you have your change of variable here, and you have your new function here now, which is a integral involving where you're integrating it with respect to capital T, right? And this function here is capital T, right? Now, this part here with the e to the minus st minus st naught. Remember, this t naught here is a constant. Minus st naught has nothing to do with the integration here, because you're integrating with respect to capital T. So you could pull out that on the outside, e to the minus st naught on the outside. And now you have the integral between infinity and 0, e to the minus st, capital T, by y of capital T dt, right? And this basically is the same integral as we had originally. It's just you have a different variable, but it's the same idea behind it. So we say here capital T was really a dummy variable. So now we could change back the capital T to the common T. So infinity 0 as the limits, e to the minus s capital T y of t, capital T rather, dt, is the integral between infinity and 0, e to the minus s common t, y of common t dt, right? And we already know what this integral here is, right? So now all we have to do is take the Laplace of this here now, which we already originally stated, is this part here, e of minus st naught by the integral of e to the minus st yt dt. And then you take the limit of this part here as r tends to infinity, and you replace the upper limit by r, where you know r tending to infinity. And this here, this part here is essentially, by definition, the Laplace of yt. So you have e to the minus st naught, the Laplace of yt, which is e to the minus st naught, capital Y of s, right? So I hope this explanation here of this proof here is clear, right? So you could go through it and make sure you understand it. Right, so let's go back to the lecture notes here now. Right, so let's look at an example. Sketch the graph of Laplace inverse of e to the minus 3s over s squared plus 1, right? Right, so this is, I just writing it on the side here. This is mine, the Laplace inverse e to the minus s t naught. So I'll put the 3 on the right hand side here. So your t naught is 3, right? So now we remember the Laplace inverse e to the minus s t naught ys is this here, the heavy side of t minus t naught y t minus t naught, right? So if we rearrange, right, e to the minus 3s over s squared plus 1, right? Basically, we take in the Laplace inverse e to the, you bring the e to the minus 3s on the outside, and you bracket the 1 over s squared plus 1, which is your ys, right? And your t naught is 3. And we know that if this is ys, 1 over s squared plus 1, we know the integral of this. Sorry, we know the Laplace inverse of this, right? This is basically the Laplace inverse, which would be sine t, right? So the Laplace inverse of the e to the minus 3s 1 over s squared plus 1 would be the Heaviside t minus 3 via t minus 3. So what if y at t is sine t, y at t minus 3 will be sine t minus 3. So the answer here is h t minus 3 sine t minus 3, right? And this is the graph here, right? So I draw a table in order to illustrate the graph because the Heaviside is of t minus 3. You know by definition, your t naught is 3. So less than t naught, the graph will be 0, right? The Heaviside will be 0. So here we have the interval t between 0 and 3. The Heaviside is defined to be 0. And anything greater than or equal to 3, the Heaviside is 1, right? So if we multiply the Heaviside by yt minus 3, basically for this first row here, multiplying 0 by this function here, sine of t minus 3, and 0 by anything is 0. And then for greater than 3 or equal to 3, the Heaviside is defined to be 1. So you're multiplying 1 by sine t minus 3, which is just sine t minus 3. So now we could sketch it here using it. It's always nice to use that to set up a table. It makes it easy to go through these steps and understand it, right? So here now you're looking at this column here now, right? Because your graph here is h at t minus 3 sine t minus 3. And for less than 3, greater or equal to 0, that is this region here, right? It's defined to be 0, so it's a horizontal line on the t-axis. And then when you hit 3, right, the graph is sine t minus 3. So you have your sine curve here now from 3 going up and down, on and on forever, right? Right, so scaling the t variable. Given a function f of t, the graph of the function f of bt, so this b here is a constant, is obtained by horizontally scaling the graph of f of t by a factor of 1 over b, given that b is not 0, right? So if b is greater than 1, the graph contracts horizontally. What do you mean by contract horizontally? It means that it's stretched vertically, basically. So you have less going across, right, of the graph, and you have more of the graph going upwards. So if you look at this example here, right, you have f of t is t squared, and f of 2t will be 4t squared, right? And you have the two graphs here drawn in the graph of t squared in green and the graph of f of 2t in blue. So if you look at the graph in blue, it's contracting horizontally, meaning it coming more together, right? And going more up. So that is why we're calling it a vertical stretch, right? Now, if the value in front, the t, was less than 1, greater than 0 but less than 1, if it was a fraction, you would have the opposite happening, right? So what will happen? It would be a vertical compression, basically, right? It will be something like this. It will come out more here on the outside, right? So if this was not 2, let me say if it was like something like f of a half t, something like that, right? So you will call this a vertical compression. Or if you want, you can say contract vertically. So this is the theorem here to explain it. Let the Laplace of y equal capital Y of S when real S is greater than A. If B is greater than 0, then the Laplace of y bt is 1 over B via SB, S over B rather. For the real S being greater than AB. Use the above scaling theorem to find the Laplace of e to the t. But we know the Laplace of e to the t is 1 over S minus 1, which is one of the earlier, the most common and straightforward results of the Laplace, right? And we know in this case here, the real of S is greater than 1, but we could just connect this result to this new theorem here we just discovered, right? So to determine e to the bt, the Laplace of that for b greater than 0. So from the scaling theorem here, real of S is greater than 1, and you have your bt now. So you know the scaling theorem says the Laplace of y r bt, right? And this case here is e r bt will be 1 over b and y of S over b. And in this case here, the y of S over b will be 1 over S over b. So you're replacing the S by S over b minus 1. And then if you multiply this here, you'll get 1 over S minus b. So your b here is this number here, whatever number this is here, right? So your real S here must be greater than 1 times b, which is b in this case. So we know that the Laplace, anything like, let me say e to the 2t, right? From before, we know that this was what? 1 over S minus 2. So in this case here, your b is the 2, right? But you're just using a different theorem to arrive at the same results. So sometimes it might be useful when you're doing different types of problems, so always have different ways of getting through the problem, then solving the problem, not just only knowing one method. Right, so now we move on to the Laplace transform of derivatives, right? So we look at a definition here. A function yt is of exponential order if there exist constants a, b, and t naught such that the absolute value of yt is less than a e to the bt when t is greater than t naught. So this is the definition of what you call exponential order. So in the beginning, we spoke about this because in order for the Laplace to be defined, the function must be of exponential order and it must be piecewise continuous, right? Show that yt is equal to t cubed is of exponential order. So first of all, right, so we have e to the bt here, this part. So we're using e to the t. So your b here is 1. So we find in our function, then our exponential function, in order to get the exponential function to be greater than the absolute value of this function here, yt, right? So if you expand e to the t, you'll get 1 plus t squared over 2 factorial plus t cubed over 3 factorial and so on, right? So this would be 1 plus t squared over 2 plus t cubed over 6 plus t to the power 4 over 24 and so on, right? So now we have on the left hand side now, right? We put in here our yt, which is t cubed, and we say that this is less than or equal to, right? This constant here that we choose is 6, and in bracket here we have all this et then, right? So this is basically et, e to the power t, right? So notice this 6 will cancel with this 6 here, right? So you'll end up getting the term t cube here on the right, but you have t cube on the left plus all these other additional terms you will get. You'll get 6 plus 6t plus 3t squared, and you'll get a term in t to the power 4 and so on. So obviously this here on the left will be less than or equal to this on the right here. In fact, it will be really less than whatever you get on the right here. So we say that the absolute value of t cubed is less than 6 to the et, right? When t is greater or equal to 0. So basically we have found our constants, right? So the constant for m, this is the m, right? Your b is 1 because e to the bt, right? And your t naught is 0, such that the absolute value of t cube is less than a to the e to the bt when t is greater than t naught. So this is a function here that is of absolute exponential order. If yt is continuous and of exponential order, and the derivative of yt is piecewise continuous on every finite interval, then the derivative, the Laplace of the derivative of yt is equal to s, the Laplace of yt minus y naught. Well, you know that the Laplace of yt is y of s, right? So now we want to look at the proof of this. So we use the basic definition again of the Laplace. So the Laplace of y derivative t is the integral between infinity and 0, e to the minus st by the function, which is y derivative t, right? And here now you're calling this here your du, you're calling this here v, and then you're integrating here, right, with by parts, right? But before we integrate by parts, we take the limit as r approaches infinity, and we replace the upper limit by r of the function. So here we have our integration by parts. Your v is e to the minus st. Your du is the derivative of yt. So therefore, if you differentiate e to the minus st, you get minus s e to the minus st dt. And if you integrate a derivative, you'll get back the original function. So u is yt, right? And remember, when you're integrating by parts, the formula, so you're taking the limit as r approaches infinity, right? This is basically uv, right? So that is e to the minus st by yt between the upper and the lower limits, which are r and 0 respectively. And then you're minus in, right? Right. All right, just give me a minute here. Okay, yeah. Sorry about that. Okay, so we back to where we were, right? So this part here is UdV. So UdV, and you remember you had a minus that, and you have a minus here. So a minus minus will give you a plus. So you have S e to the minus st by yt. The s, you're not integrating in respect to the s, so the double negative gives you a positive here. So you could integrate here between r and 0, e to the minus st yt, right? So this here, you take the limit as r approaches infinity, and this part here on the right-hand side is basically, by definition, the Laplace of yt. And then on the left-hand side, now you're plugging the limits here as r tends to infinity. So the upper limit is r. So you have e to the minus sr, y of r, and then e to the minus s0, which is 1, right? Y of 0, so you're minusing that, right? Of course, here, if you have a exponential to a negative power here and you're approaching infinity, this will be 1 over the exponential to the positive power here approaching in infinity. So this entire part here will drop out. This part will approach 0. So what you have surviving, basically, you have this here, your minus y naught, and you have your s of your Laplace of yt. So that is your s of, you just rearrange it, and you have s of y of, s of the Laplace of yt minus y naught. And from this, you could derive higher derivatives, right? So you could derive y of double prime t as the Laplace of y of the first derivative t prime on the outside here, right? So you're using the same, the original result. So this will be s of Laplace of y prime t y minus y prime 0. All you're doing here is you're having a prime on the t and a prime on the 0, right? From the first result. So you're using the first result to derive higher derivatives, the Laplace of higher derivatives. So now you take the Laplace of y prime t. We already know this result here. This is s of L of yt minus y naught. And you have s on the outside to multiply by that. So you end up with a s squared L of yt minus s of y naught, and then minus y prime 0 here, right? So this, the Laplace of the second derivative and the Laplace of the first derivative, you will find this in your table of Laplace transform, right? Or you could even use this here to derive the Laplace of the third derivative. So a good exercise for you to do is take the third derivative and derive it from the second derivative and make your substitutions, right? So the theorem states if you have y of t, the first derivative of y of t, the second derivative, the n minus 1 derivative, and all these derivatives are continuous and of exponential order, and ynt, the n derivative, is piecewise continuous on every finite interval, then the Laplace of the n derivative of t is s to the n y of, the Laplace of y of t minus s to the n minus 1 y naught minus s to the n minus 2 y prime naught dot dot dot, all these terms in between minus s y to the n minus 1 of 0 minus y to the n minus 1 of 0. Right, so this extended result here is not really required, right? Solving differential equations. We apply the above formulae for the Laplace of y prime t and y double prime t, and the Laplace of y to the n derivative t in the solution of initial value problems, right? So we're looking at some initial value problems here now. Solve the initial value problem, right? So these are differential equations here. So you have the second derivative of y minus 3 by the first derivative of y plus 2y is equal to e to the 3t. And you have your initial conditions here, y naught is 0, y prime naught is 0. So these two are 0. So you take the Laplace transform throughout this entire equation on both sides, right? So you have the Laplace of y double prime minus 3 by y prime plus 2y is equal to the Laplace of e to the 3t, right? So therefore, you remember the Laplace operator is linear, right? It have a linearity property in it. So you're taking the Laplace of y double prime minus 3 times the Laplace of y prime plus 2 times the Laplace of y is equal to the Laplace of e to the 3t. So your Laplace of y double prime is s squared Laplace of y minus s y naught minus y prime naught. And your Laplace of y, sorry, your Laplace of y double prime is this here, all the way up to this. And the Laplace of y prime is s Laplace of y minus y naught, right? And then you substitute your initial condition. So this here, remember y naught is 0, y prime naught is 0. So this term here will be 0, this will be 0, and this here will also be 0. So look at it here substituted. And then you're taking your 2 times the Laplace of y and the Laplace of 3t, e to the 3t on the right hand side. So this is 0, 0, and you're seeing what's happening here, right? So what you could do now, you could collect all the terms here with common factors. So this have Laplace of y, and this have Laplace of y in it here. So that the Laplace of y here now will be s squared minus 3s plus 2 in bracket L of y, or the Laplace of y. And the Laplace of e to the 3t we know is 1 over s minus 3, right? So therefore the Laplace of y will be 1 over s minus 3 by s squared minus 3s plus 2, right? So now we want to evaluate the Laplace inverse of this function here on the right. So before we could do this now, remember we had to use the partial fraction breakdown for this here. Last day I showed you a table with the various partial fraction breakdowns, right? So when you have a simple factors, it will be a constant over the simple factors and you add them up, right? Now this here, this quadratic here is a reducible quadratic. So if you notice here, this could factorize into s minus 1, s minus 2. So you end up here with 3 simple factors. So therefore the partial fraction breakdown would be a over s minus 1 plus b over s minus 2 plus c over s minus 3, right? And now what you do here, in order to find your constants, you multiply throughout this entire equation by s minus 1, s minus 2, and s minus 3. So of course, if you multiply the left hand side by s minus 3, s minus 2, s minus 1, it will cancel. And you will just get 1 on the left hand side. And if you do it on the right hand side, the s minus 1 will cancel, right? So you'll have a by s minus 2, s minus 3. The s minus 2 will cancel with this term here. So you'll have b by s minus 1, s minus 3. And the s minus 3 will cancel here. So you'll have c by s minus 1, s minus 2. Right? So now we need to find the constants, right? So the best way to do this is to try to eliminate some of the other constants in order to solve for one constant at a time. So if I substitute s equal to 1, look at this, have s minus 1 in it, so this will be 0. So this term will disappear, and this c will also be 0. That will disappear. So you'll have 1 minus 2 is minus 1, and 1 minus 3 is minus 2. So minus 1 by minus 2 is plus 2 by a is equal to 1. You see it here? So a is a half. So we get a, right? So now let's put s equal 2. Well, this will be 0. So all this will disappear, right? This here will be 0 because you have 2 minus 2, 0. And then this here, you'll have 2 minus 1 is 1. And then you have 2 minus 3 is minus 1. So you'll have minus b here basically is 1. So b is minus 1. And finally, you put s equal 3. This will disappear because 3 minus 3 is 0. This second term here will disappear as well, right? And you'll have 3 minus 1 is 2. And 3 minus 1 is 1. So you'll have 2c is equal to 1. So c is a half. So therefore, you'll have a half into 1 over s minus 1, because this is your a, minus b, which is minus 1. So 1 over s minus 2 plus c over s minus 3, which is a half into 1 over s minus 3. So the Laplace inverse of 1 over s minus 1 is e to the t. So a half by e to the t. The Laplace inverse of 1 over s minus 2 is e to the minus 2t. So you have negative e to the minus 2t. And the Laplace inverse of 1 over s minus 3 is e to the 3t. And you have a half to multiply by it. So that gives you the result there. So this is your y of t. Right? So we're looking at digression now of piecewise defined functions. Okay. So we previously determined the Laplace transform of piecewise defined functions, such as y of t is 0 between 0 and 1, t between 1 and 2, and 0 between 2 and infinity, which is the same as saying greater or equal to 2, right? So I just wrote that in here to show you that this is the same as t greater or equal to 2. And we did this using the definition of Laplace transform. Right? So let's look at this here now. Recall from page 25, we had the Laplace, the integral between infinity and 0, e to the minus s t y t, right? So we're breaking up this function into the 3 pieces, right? It's 0 between 1 and 0, it's t between 1 and 2, and it's 0 between infinity and 2. So you're breaking it up, the integral between 1 and 0, between 2 and 1, and between infinity and 2, right? So here now, you'll have 0 because you're multiplying e to the minus st by 0. So here we'll get 0. In the middle part, you'll have e to the minus st by, the function is defined to be t in this region. And the third region, between infinity and 0, the function is 0. Sorry, between infinity and 2, the function is 0. So therefore, this first part and the third part here will drop off, and you'll only have the middle part here surviving, right? So in order to integrate here now, you apply your normal integration by parts, right? So I call in the TV, and I call in the e to the minus st du, right? So I wrote it here on the left-hand side. If v is t, then dv is 1, right? Well, it's 1 dt, right? If du is e to the minus st, then when you integrate that, you'll get minus e to the minus st over s, right? So uv. So that is minus t to the minus st over s, look at here, right? And you're taking the limits here as t equal 2 and t equal 1. And then you're subtracting u of dv, or u by dv. So that is this here, right? Minus e to the minus st over s by 1. And then you have to subtract that. So minus will be plus. So basically, you're just integrating e to the minus st, because you could pull the 1 over s on the outside, because this is has nothing to do with the integral. The integral is with respect to t, not respect to s. So if I put in my upper limit here, I'll get minus 2 e to the minus 2s over s. And then after minus 1, which is plus 1 e to the minus 1s. So that is e to the minus s over s. So that is what I'll get here with this when I plug in the limits here. When I integrate e to the minus st, I'll get minus e to the minus st over s, right? And then I have to plug in the limits here, right? 2 and 1. So I'll get minus e to the minus 2s over s, and I'll multiply it by another s on the outside. So that will be s squared. So e to the minus minus e to the minus 2s over s squared. And then I'm subtracting this here with 1. So a minus will give me a plus e to the minus s over s by another s on the outside, which is s squared. So that is how I got these 4 terms here. And basically this here, we just group them accordingly. So e to the minus s as a common factor, you'll have 1 over s plus 1 over s squared. And then minus e to the minus 2s, you'll have 2 over s plus 1 over s squared. Right? So that is how we arrive at this result here. So in between, I just put in little substitutions and the integration by parts to guide you. So we would now consider an alternative method of evaluating the Laplace transform of a piecewise defined function, where we would use the Heaviside step function, right? So this is the theory behind evaluating the Laplace transform of piecewise functions using the Heaviside function, right? So we have a general piecewise function defined, right? So we have the function here defined in 4 parts here, right? So f of t is f1t between 0 and t1. It's f2t between t1 and t2, and so on. Fn minus t between tn minus 2 and tn minus 1, and fnt between tn minus 1 and infinity, right? So in other words, this is just greater than or equal to t minus 1, right? And I said 4 parts, but this is actually n parts, right? Because this is the general proposition for the piecewise defined function. When we're looking at specific examples, we will see, depending on how many parts we have, it might have 3 parts, it might have 4 parts, it might have 2 parts, as the case might be, right? So this is how it's been expressed. So your function, in order for you to evaluate the Laplace transform, you have to take for each piece of the function, for each individual piece, right? You're taking the Heaviside at the lower limit, right? And you're minusing the Heaviside at the higher limit, right? So basically, this is the Heaviside here of T naught. So the T naught here will be 0, right? So your T naught here is 0, and your T naught here is your T naught here is T1, right? So this will be the Heaviside at this endpoint here, T minus 0, minus the Heaviside at this endpoint here, T minus T1, right? So this works out to just be the Heaviside at T. Right, so if I draw a little graph here to illustrate the Heaviside, right? And let's say the graph, you know, we define is 0, anything, so this is your 0 here, right? And anything greater or equal to 0, it could be 1. So that is 1 here, right? So h T minus 0, right, will be 0 on this side here. But as it hits 0, it will be 1, right? So HRT is really 1 then. That is why I put an arrow here to show that HRT, T minus 0 is 1. And then you have minus HRT minus T1. Multiply by your function here for this piece here, F1T. And then the same thing happening with the other pieces. HRT minus T1 minus HRT minus T2, the two endpoints, the Heaviside of the difference of the two endpoints by the function in that region. And so on, right? Until you reach all the way up to the last region. This is the last region here. So this will be HRT minus Tn minus 1. And this here will be HR, the Heaviside of T minus infinity. Right. Now, if you notice here, if the Heaviside steps up when it reaches infinity, because this is your T naught, infinity is your T naught. So which means the Heaviside on 0 until it reaches infinity. And when it reaches infinity, then it will step up to 1. So you notice what happening there. So this here, the definition of HRT minus infinity is really 0. Because the function will never reach infinity, right? So this basically saying if it reaches infinity, then it will step up to 1. So that is why this part here just had the HRT minus Tn minus 1 by the function, because this part here will be 0. So that doesn't give you any contribution, right? So this will help you in order to evaluate problems involving piecewise where you're using the Laplace and the Heaviside function. Right, so let's look at a specific example here now. So this piecewise function defined in 4 parts, 1, 2, 3, 4. Right? And you're seeing what's going on here, right? So the first part here, this is going to be h t minus 0 minus hr t minus 2. You seen it here? But hr t is always defined to be 1, as I just explained. And then you have to multiply that by f1t. And then the second part, hrt minus 2 minus hrt minus 5, because these are the two endpoints here. Multiply by f2t. And then again plus hrt minus 5 minus h at t minus 6 by f3t. And finally, h at t minus 6 by f4t, because this part here, h at t minus infinity is 0, as I just explained. Right, so we're doing an example now. Find the Laplace transform of the function f of t, defined to be t when t is between 0 and 1, and 1 when t is between 1 and infinity, right? So in your f is only have to remember your f1t here, and this is your f2t, right? So that it will be 1 minus h at t minus 1 by f1t, which is t, plus h at t minus 1 by f2t, which is 1, right? So, of course, this here, equation 18, we could use the Laplace of the Heaviside here, this definition here, right? This theorem here, rather, right? H at t minus t naught by the function t minus t naught is equal to e to the minus s t naught by y of s, right? So let's rearrange it here, right? So look at this here. Now, if we multiply t by 1 here, we'll get t, right? And then we'll end up with t by h at t minus 1 and h at t minus 1. So these two parts here, the second and the third part here, will have h at t minus 1 in common, right? So h at t minus 1 is a common factor, right? And then you will have t minus 1 on the inside, because so you'll get back your original value here. Look at it here, minus h at t minus 1 by t minus 1. So if you multiply this here by your t, you'll get back the t, the minus h at t minus 1 by t. And if you multiply this by negative 1, a negative by negative is a positive, you'll get back your h t minus 1. Right, so so this is a little tricky here. We have to know to arrange it in this form here, where you have a Heaviside by a function then. So we could evaluate using the Laplace. So now we take the Laplace of this here now, the Laplace at t minus h at t minus 1, t minus 1. And we use the linearity property. So this will be the Laplace at t minus the Laplace at h at t minus 1, t minus 1. So this is your Heaviside here, and this is your y at t minus 1. And the Laplace at t is 1 over s squared. We know that, right? Remember, the Laplace at t is t to the power n is n factorial over s to the n plus 1. So your n factorial is the 1, and the 1 plus 1 is 2. So you get 1 over s squared. And then the Laplace of this here, right, is minus s t naught, right? And your t naught here is 1. So you have minus s over s squared, because the Laplace at this here is 1 over s squared. So let's look at another example here. Find the Laplace transform of this piecewise function. So it's defined to be 0 between 3 and 0. It's defined to be e to the power t between 3 and 4, and it's defined to be 0 between 4 and infinity. Right? So we're using it. We're expressing it in terms of the Heaviside step function. So we take in h at t minus h at t minus 3, which is 1 minus h at t minus 3 by the function defined in that region, which is 0. And then the second region would be h at t minus 3 minus h at t minus 4 by e to the power t. And then the third region will just be h at t minus 4 by 0. So these two parts here wouldn't give anything. So it's just the middle region. So we have h at t minus 3 minus h at t minus 4 e to the t. So h at t minus 3 e to the t minus h at t minus 4 e to the t. Now, in order for us to evaluate this using the Laplace, somewhere you have to bring in a minus 3 here with this part here, with your y. So this is your y and this is your y here. Remember the Heaviside definition is h to the t minus t naught, y to the t minus t naught. So what we do here, we use the lower exponents, right? Or the lower indices. So this e to the t, we could break it up as e to the t minus 3 e to the 3. And similarly, the e to the t here, we could break it up as t minus 4 e to the 4, because when you add these exponents here, they will cancel and you'll get back e to the t. Why are we doing that? Because we need t to the t minus 4 in this part here with your y, and you also need t minus 3 in this part here for you to apply the definition of the Laplace using the Heaviside. So you see, recall h at t minus t naught, y at t minus t naught is e to the minus s t naught, the Laplace of yt. So at doing that here, basically you have the Laplace of h t minus 3 e to the t minus 3 e to the power 3. Well, e to the power 3 is a constant, so I could just pull out on the outside, right? And similarly here, e to the minus 4, I could pull out on the outside. So I have my Heaviside here with my function in the required form in both cases, right? Look at them here carefully. So according to the Laplace, this will be e to the minus 3s, the Laplace of e to the t. And this will be e to the minus 4s, the Laplace of e to the t. So I get e to the 3, e to the minus 3s over s minus 1, e to the 4 minus e to the 4, e to the minus 4s over s minus 1. Right, and then I could just factor the 1 over s, and I'll have e to the minus 3s minus 1 minus e to the minus 4s minus 1. Right? So I just want to pause here a little while here for you to absorb everything that we went through here. Right? And if you have any questions, you could ask me. Right? I'll give you a few moments and then we'll continue. Yeah, nothing so far. All right, so okay, we now use the Laplace transform to solve a second order differential equation. Right, so we have how do we identify a second order differential equation? Well, the highest power of the derivative is 2. So you see you have a y double prime plus by prime plus cy is equal to f of t. So the highest power of the derivative here is 2. So therefore, it's a second order differential equation. And they say here that the capital F of t, the function on the right-hand side of the equation here, is discontinuous. So we have an example here of a second order differential equation. X double prime t plus xt is equal to f of t. And we have subject to the initial conditions. X naught is 0 and x prime naught is 1. Right? And f of t is piecewise defined. F of t is 1 between 0 and pi over 2. And it's 0 when t is greater or equal to pi over 2. So to go about this here now, we take the Laplace on both sides of the equation, of the differential equation. So we take in the Laplace of x double prime t plus xt, and we take in the Laplace of f of t. Remember, the f of t is piecewise defined, so we want to deal with the f of t first, right? And we want to use the Heaviside function in order to evaluate the piecewise function then. So use the Heaviside to express it in that form, right? So remember, this is how it's defined. So you're taking the Heaviside t minus t naught, which is t minus 0. So that is h at t. And you're taking the Heaviside at this endpoint here, t minus pi over 2. And you're multiplying it by 1. So of course, you know, h at t minus 0 is 1. Minus h at t minus pi over 2, and you have to multiply that within this piece here, and within this region here is defined to be 1. And then in the other region, h at t minus pi over 2 is 0. So this part here will drop off, so you just have this part here surviving, right? And we know that if you take the Laplace inverse of if you take the Laplace of 1, you will get 1 over s, and if you take the Laplace of the Heaviside, you will just get e to the minus s t naught over s, and your t naught here is pi over 2. So you have e to the minus s pi over 2 over s. So we now have this right-hand side. So we could put it into the equation, and now we deal with the left-hand side, right? So we're using the Laplace of derivatives here now, which we just went through, right? So x double prime, the Laplace of that is s squared. The Laplace of x minus s of x naught minus x prime naught, plus the Laplace of x is 1 over s, or is equal to 1 over s minus e to the minus s pi over 2 divided by s, right? And now we plug in the initial conditions. This term here is 0, this one is 1, right? X naught is 0 and x prime naught is 1. So you're putting in 0 here, so this term will drop out, right? This one you're seeing minus 1 plus the Laplace of x. So you factor the Laplace, you'll get s. You put the 1 on the right-hand side here. So this minus 1 goes across here, right? So that will be plus 1. So you have s squared, the Laplace of x plus the Laplace of x, which is s squared plus 1 in bracket the Laplace of x. 1 plus 1 over s minus e to the minus s pi over 2 over s. So the Laplace of x will be all these terms on the right divided by s squared over 1. So you see we have that here. So you have 1 over s squared plus 1, 1 over s into s squared plus 1 minus e to the minus s pi over 2 divided by s in the s squared plus 1. Now it's easy to evaluate this one here, right? We know that this part here, the Laplace inverse of s squared, 1 over s squared plus 1, would be sine t, right? But this part and this part here, we need to apply partial fractions in order to find the constants on top. So we have 1 over s into s squared plus 1 is equal to a over s, right? So the s is a simple factor, but the s squared plus 1 is an irreducible quadratic factor. So when you have an irreducible quadratic factor, it will be a constant by s plus another constant. So you have a over s plus bs plus c over s squared plus 1. And then you multiply throughout by s squared plus 1. So on the left hand side, you'll get 1. On the right hand side, you'll get a into s squared plus 1 because the s will cancel. And then the s squared plus 1 will cancel in this term here. So you'll get bs plus c by s, right? And we apply a technique now called equating coefficients, right? So you collect all the terms in x squared, s squared rather, all the terms in s and all the terms that don't have any s in it. So basically that will be s to the power 0. So those are like the constant values, right? So you have a plus b s squared plus cs. When you expand this out, right, the coefficient s squared is a plus b on the right. If you notice on the left, you don't have any s squared. So which means the coefficient of that had to be 0. So a plus b is 0. The coefficient of s on the right is c. You don't have no s on the left. So that means c is 0. And the coefficient of s to the power 0, right? Which is just like a constant then, because s to the power 0 is 1. So you have a on the right and you don't have any s on the left. So the coefficient of s naught, s to the power 0 is 1. So a is 1. So a plus b is 0. So 1 minus 1 is 0. So b is minus 1. So therefore, this here would be 1 over s minus s over s squared plus 1 because the c is 0, right? And remember your second term, right? Your second term that is this here is similar to the third term, right? The only difference in the third term, you have e to the minus s pi over 2. So all you have to do is factor over that and it will have the same constants in terms of your partial fraction breakdown. So look at it here. 1 over s squared plus 1, that is the first term, plus 1 over s, which is the partial fraction breakdown of this, minus s over s squared plus 1. And then for the third term, you just, the third term is negative, right? So you have a negative, so you just factor the minus e to the minus s pi over 2 in bracket 1 over s, which is from the second part, minus s over s squared plus 1. And all you have to do now is take the Laplace inverse of all these terms here. So the Laplace inverse of the first term here is sine t. The Laplace inverse of 1 over s is 1. The Laplace inverse of s over s squared plus 1 is minus cos. Well, it have a minus here. So it's minus cos t. And the Laplace of this part here, right? Right, that is e to the minus s pi over 2, 1 over s will be the Laplace, sorry, would be minus the Heaviside t minus pi over 2 by 1 because the Laplace inverse of 1 over s is 1. And then it will be like plus, because minus are plus. So it will be the same Heaviside t minus pi over 2 And the Laplace inverse of this here is what? The Laplace inverse of this function is cos t, right? But because this part here have a pi over 2 in it, you have to write it as cos pi minus pi over 2. Sorry, cos t minus pi over 2. According to the definition, because you remember the Heaviside function, when you're finding the inverse Laplace, whatever your t naught here, your y at t minus t naught must match up. So the Laplace inverse of s over s squared plus 1 is cos t. So you have to replace the cos t by t minus pi over 2. So therefore you'll get back all the terms here, you'll get minus ht minus pi over 2 by 1, and you'll get plus, because minus minus is a plus. H of t minus pi over 2, cos of t minus pi over 2. So that is the end result there of that equation, right? So we come now to some of the topics here, some of the questions that we are going to look at in order for you to for your midterm review, which is your online assessment that you'll be getting, right? So we use the formulae. LRY prime is S LRY, right? Minus Y naught. LRY double prime is S squared L of Y minus S Y naught minus Y prime naught. To solve the following initial value problems. Use the Laplace transform to solve Y double prime minus 10 Y prime plus 9 Y equal 5t. Subject to the conditions Y naught is minus 1 and Y prime naught is 2, right? So you're taking the Laplace of everything on the left and everything on the right. Right, so you know this is your first step here. Then you use your linearity property, right? So therefore the Laplace of Y double prime will be Y squared, sorry, S squared Laplace of Y minus S naught minus SY naught minus Y prime naught. And then this will be minus 10, and the Laplace of Y prime will be S Laplace of Y minus Y naught. You could put that in bracket, and then plus 9 the Laplace of Y, and the Laplace of 5t is 5 over S squared. You could pull out the 5, and you're taking the Laplace of t, and the Laplace of t is 1 over S squared, so it's 5 over S squared, right? So now, remember your Y naught is minus 1. So a minus by a minus is a plus, so you get plus S here. And your Y prime naught is 2, so you have minus 2. Minus 10S, Laplace of Y minus 10. This here is minus Y naught. Remember your Y naught was what? Minus 1, right? So if you put a minus 1 here, that will be a plus 1, right? And then you have to multiply that by minus 10, so you'll end up with minus 10. Plus 9 Laplace of Y equal 5 over S squared. So minus 2 minus 10 is minus 12, right? And you carry that on the right hand side, you'll get plus 12. And you could also carry the plus S on this side here, so you get minus S. So you end up with S squared minus 10S plus 9 by the Laplace of Y. And then the Laplace of Y will be all this on the right divided by s squared minus 10s plus 9. So 5 over s squared multiply by s squared minus 10s plus 9, right? And then to make this the LCM, you gotta multiply s squared. Sorry, you gotta multiply. Right. So let me just put in a extra step here. Right, so this is 5 minus s to the power 3 plus 12 s squared. So that is what we was done here. So therefore, the s squared into s squared minus 10s plus 9 would be the LCM of every term on the top here. To make it easier then. And if you notice here, this s squared minus 10s plus 9 could be factorized. Is a reducible quadratic factor. So you end up with two simple factors then, right? Now this is a repeated factor. S squared is a repeated simple factor. So according to the partial fraction breakdown, when you have a repeated single factor, you have to take a constant divided by s, and then you take another constant, add it to another constant divided by the factor to the power 2. Right? So look at here. A over s plus b over s squared. And then the other two factors, c over s minus 1 plus d over s minus 9. So that would be breakdown for the entire rational expression. Right? So look at now, we multiply throughout the entire equation by s squared, s minus 1, s minus 9. So the s will cancel, so you'll end up everything on the left hand side will cancel with the denominators here. So you'll just get minus s to the power 3 plus 12s squared plus 5. And here now, one of your s here will cancel with this s, so you'll get s minus 1, s minus 9 by 8. The s squared will cancel, you'll get b s minus 1 by s minus 9. The s minus 1 will cancel with the c. So you'll get cs squared, right? S minus 9, and the s minus 9 will cancel with the d, so you'll get ds squared by s minus 1, right? So I just wrote out the expansion here back, as by s squared minus 10s plus 9 plus b by s squared minus 10s plus 9 plus cs squared s minus 9 ds squared s minus 1, right? So why did this here? Looking at the equating coefficients here, right? But equally, you could just put in values and work it out, right? So if you put in s equal 1, right? If you put in s equal 1, 1 minus 1 is 0. So this entire term here will vanish. This entire term will vanish because this is s minus 1, and the last term will vanish. So if s is 1, you'll have what? You'll have minus 8 here, right? 1 squared is 1. So you'll have minus 8c. Look at here, right? On the left, on the right rather. And then on the left here, you'll have to put in 1. So you'll have minus 1 plus 12 plus 5. So 12 and 5 is 17, minus 1 is 16, right? So 16 over minus 8 is minus 2. right? Now, if you put s equals 0, so this will be 0 here. So anything by 0 is 0. This will be 0 here, and this will also be 0 here, right? So A, D, and C will disappear, right? So the only surviving term you'll have is this term here. So you'll have -1 by -9, which is +9. So 9b will be 5, right? So b will be 5/9, right? And then here now, if you put s equal 9, this term will vanish. This term will vanish. The second term, the third term will vanish. The fourth term will survive. So nine minus 1 is 8. And 9 squared is 81. So you have 8 by 81d. So this will give us some big values, right? You'll have 9 cubed is 729, and you have a negative in front of it, right? 9 squared, 81 by 12 is 972 plus 5. So on the left hand side here, you get 248. The right hand side here, 248 could divide 8, you get 31. So you get 81d is 31. So d is 31 over 81. Right? So we end up getting B, C, and D, but we didn't get A, right? So there's not really any value we could substitute to get A. So what we have to do now, we have to equate coefficients in order to get A. So that is why I underline AS by S squared here. So this will give you a AS cube. The CS squared by the S here will give you a CS cube, and the ds squared by s here will give you a ds cube, right? Now notice on the left hand side of the equation, this is s cube. So the value in front, s cube, is, you see now, minus there, so it's -1, right? So if you equate coefficients, basically you'll get a plus c plus d. You see that here is equal to -1. And we already know what C and D are. D is 31 over 81. C is -2, right? So A would be -1 minus C minus D. So that is -1 minus -2, which is +2. And you're minusing 31 over 81. So that will give you 1 minus 31 over 81, which is 50 over 81. So you have your partial fraction breakdown here. A over S, B over S squared, C over S minus 1, and D over S minus 9. So A over S, B over S squared, C is -2 over S minus 1, and D over S minus 9. So all you do is you factor out those constants. You have 1 over S, 1 over S squared, 1 over S minus 1, and so on, 1 over S minus 9. And then if you take the Laplace of 1 over S, you'll get what? 1. So that will just give you 50 over 81. You take the Laplace of 1 over S squared, you'll get T, so 5 over 9 by T. The Laplace of 1 over S minus 1 is e to the T, so you get -2 e to the T. And the Laplace 31 over 81 is, sorry, the Laplace of 1 over S minus 9 is e to the 9t. So you have 31 over 81 e to the 9t. Right, so this is our problem from the Theorem. Now I have I went through quite a number of the problems suggested in the course web page, right? These problems are from Finan, right? Some of the problems in Finan, all the problems in Finan, they have solutions to them, but some of the solutions might be kind of missing some of the steps, right? So what I have done, I've wrote down some of the solutions, including all additional steps, right, to help guide you. So some of those problems we'll be going through most likely in the next session on Friday. So we're looking at some here in the meantime. Problem 44.18, page 26. The graph of FT is, so you notice this graph here is like a step, right? So between infinity and 1, it defined to be 0, right? So I could probably write the definition for these values here. So I'm going to use a different color here. So here the graph is defined to be 0. Here the graph is defined to be 1. Here the graph is defined to be 2. And here is defined to be 0 again, right? So it's piecewise defined. So we want to represent this as a combination of Heaviside step functions and determine the Laplace transform, right? So you see, look at it here. Exactly what I wrote here in the diagram. So f of t is 0, right? Between 0 and 1, right? Is 1 between 1 and 2. Is 2 between 2 and 3. And is 0 between 3 and infinity. Beyond 3 basically, right? So f of t is the Heaviside at t minus 0, which is 1, minus the Heaviside at t minus t1 by the function defined in that region. And then you're adding that to the Heaviside at t minus t1 minus the Heaviside at t minus t2 multiplied by the function in that region, plus the Heaviside at t minus t2 minus the Heaviside at t minus t3 in that third region, the function multiplied by that. And then finally, you're adding it to the Heaviside at t minus t3 by the fourth region, the function within the fourth region, right? So in the first region here is 0. So this part will drop out. The second region, how is all the function defined to be 1? So this part will survive. The third region, the function is 2, so you're multiplying 2 by the difference of these two Heavisides. And the fourth region, the function is 0, so this part will drop out as well. So basically, you'll get the Heaviside t minus 1 minus the Heaviside at t minus 2 because you're multiplying by 1. Plus the 2 times the Heaviside at t minus 2 minus 2 times the Heaviside at t minus 3, right? And of course, these two in the middle here would simplify to the Heaviside t minus 2 because you have a 2 here and you have a minus 1. 2 minus 1 is 1. So that is the Heaviside at t minus 2. Plus the Heaviside at t minus 1 minus 2 times the Heaviside at t minus 3. And then the Laplace of ft, right? You take the Laplace of each one of these functions here. And we know that the Laplace of the Heaviside is e to the minus t0 over s. And your s here is 1, right? Sorry, your t0 is 1. So you have e to the minus s over s. And then your t0 here is 2. So you have e to the minus 2s over s. And then you have a 2 in front here. And your t0 here is 3. So you have 2 minus 2 by e to the minus 3s over s. So that was our problem in Finan, right? This is 44.18, right? So another problem, 44.10. The Laplace inverse of e to the 3 minus 3s into 2s plus 7 over s squared plus 16, right? So remember when you're finding the Laplace inverse, right? What I do, I circle this part here, because you could find the Laplace inverse of minus 3, or the Laplace inverse of minus s t naught. And in this case here, your t naught is 3 by y of s. So this here is my y of s. And here now you could use the t-shift formula, right? Look at it here, right? So Laplace inverse of e to the minus s t naught ys is the Heaviside t minus t naught by the function t minus t naught, right? So that is why this here, I identified this here to be my ys, right? And I just said that the t naught here is 3, right? And the ys is 2s plus 7 over s squared plus 16, right? So this part here, right, we could break it up as 2s over s squared plus 16 plus 7 over s squared plus 16. And we could further separate the 2 here. So this will be 2 by s squared, sorry, 2 by s over s squared plus 4 squared, right? Why are doing that? Because you remember the rule to find the Laplace inverse of a function of this form, and then plus I break up before the 16 here as 4 squared, but I need a 4 at the top here, right? Because I know the Laplace of s over s squared plus 4 squared. The Laplace inverse of this is cos 4t, and the Laplace inverse of this is sin 4t, right? So now remember on top here are 7, right? So I pull out the 7, and then this here will give me 4 here, so I divide by 4 here, right? You see exactly that's been done here. Watch it here. So this will be the Laplace inverse of s over s squared plus 4 squared. So that is 2 by cos 4t plus 7 over 4 sin 4t. So that is your yt, right? But remember your Laplace inverse of e to the minus 3s into 2s plus 7 over s squared plus 16 would be your h at t minus t naught, and your t naught is 3, by your y at t minus t naught, which is 3. This is yt, right? So in order for this to be yt minus 3, you have to apply a shift where you're seeing your t's here, right? So that will be the Heaviside t minus 3, the 2 cos 4 by t minus 3, so the t shifted t minus 3, and then the 7 over 4 sine 4 by t minus 3. So you just shift the t to the minus 3 based on the definition and the how to evaluate the Laplace of a Heaviside. Example, next example here. Y double prime plus 2y prime plus y is ft. Given initial conditions, y naught 1, y naught is equal to 1, and y prime naught is equal to 0, where ft is 1 between 0 and 2, and ft is 0 between 2 and infinity. So we're using the piecewise definition with the Heaviside. So here you'll have to multiply h of t. So you'll have your brackets here, your h of t minus h of t minus 2 by 1. And here you'll have your h of t minus 2, right, by 0. So this part won't give you any contribution, right? Look, it's written here. 1 by h of t minus t, 1 by f1t, plus h of t minus t2 by f2t. So this part here, 1 by h of t minus 1, because h of t is 1. And then this h of t minus 2 by 0. This part drops out. So you take your Laplace of 1 and your Laplace of h of t minus 2. So your Laplace of 1 is 1 over s, and your Laplace of h of t minus 2 is e to the minus 2s over s. That is the right hand side. Now we're dealing with the left hand side. So the left hand side, again, we apply the rule for the Laplace of the second and first derivative and use the linearity property, right? Now, remember the Laplace table will give you look at the table here. You see the Laplace of the first derivative of t and the second derivative of t. Right, so these will be given in a table, so you don't really have to remember that. But it's always good to remember it because it makes life easier for you. So you have s squared L of y for the Laplace of y minus s y naught minus y prime naught plus 2 s of the Laplace of y minus y naught, and you have to multiply all that by 2, and then plus the Laplace of y, right? So you make your substitution here, your y naught here is 1, and your y prime naught is 0. So that will be minus s by 1, which is minus s. This will be 0. This will be 2 by s Laplace of y minus 1. So this s here, this minus s, you could carry it on the right hand side, so you get plus s, right? The 2 by the minus 1 will give you minus 2, so you could carry that over, you'll get plus 2. So you'll get s plus 2 plus 1 over s minus e to the minus 2s over s, which we worked out slightly above the right hand side of the Laplace of the differential equation, right? And then you factor the the Laplace y on the left hand side, you'll get s squared plus 2s plus 1. So you divide all the terms on the right now by s squared plus 2s plus 1. So you'll get 2s plus 2 over s plus 1 squared. You'll get 1 over s into s plus 1 squared, and you'll get e to the minus 2s over s into s plus 1 squared. So this s plus 2 here, right, could be written as s plus 1 over s plus 1 squared. So you could break up this into two terms. You'll get s plus 1 over s plus 1 squared. So that'll just be 1 over s plus 1. And then you'll have 1 over s plus 1 squared plus 1 over s into s plus 1 squared minus e to the minus 2s over s into s plus 1 squared, right? So now we want to use partial fractions here. So we could evaluate this part here, right? But this part here, the third and the third part, which is similar to the fourth part, they are the same denominator, right? These are two simple factors here, but this is a repeated simple factor. So it will be a over s, b over the other simple factor, s plus 1, plus c over the s plus 1 squared. And if you multiply now throughout the equation here by s plus 1 squared, you'll get 1 on the left, you'll get s plus 1 squared by a, you'll get bs by s plus 1, and then you'll get c by s here. If you put s to be 0, this part and this part here go drop out. So you'll just get 1, a is 1, so a is 1. If you put c to be minus 1, sorry, s to be minus 1, minus this part will be 0, and this part here will also be 0. You'll get minus c is 1, so c is minus 1. And then now, in order to evaluate the b, you need to equate coefficients. So here, you'll have a as squared plus a bs squared. So when you expand this out and you expand the first and the second term, you'll end up with a bs squared. You'll end up with a, because you'll get s squared here, so you'll end up with as squared. So a plus b s squared. And you have nothing on the left hand side in terms of s squared. So s squared here on the left hand side, the coefficient ought to be 0, right? Since you have no term in s squared here, it means that the coefficient ought to be 0, the value in front of it. So a plus b is 0, you seen it here? And we already found a to be 1, so 1 minus 1 is 0, so b is minus 1. So 1 over s into s plus 1 squared is 1 over s minus b. So minus 1 over s plus 1, and c is also minus 1 over s plus 1 squared. Right? So this is what we end up with, 1 over s plus 1 plus 1 over s plus 1 squared plus 1 over s into s plus 1 squared minus e to the minus 2s into 1 over s into s plus 1 squared. So this term here, from this third term here, from this term to here, we get these three terms above here. So you get 1 over s minus 1 over s plus 1 minus 1 over s plus 1 squared. And you notice something, this 1 over s plus 1 will cancel with this minus 1 over s plus 1. This 1 over s plus 1 squared will cancel with the minus 1 over s plus 1 squared. So you just add the 1 over s, and then this e to the minus 2s into 1 over s into s plus 1 squared. And we already know that this here, the partial fraction breakdown for this is these three terms here. So 1 over s minus 1 over s plus 1 minus 1 over s plus 1 squared. So you'll have 1 over s minus e to the minus 2s into 1 over s minus 1 over s plus 1 minus 1 over s plus 1 squared, right? And then the Laplace inverse of 1 over s is 1. And the Laplace inverse of all this here, right? Because your t naught is 2, is the heavy side at t minus 2. And we know that this is 1. We know that this is e to the minus minus, right? Because this is supposed to be minus. So the pluses are minus minus. So it means that your t here is 2. So because this is t minus 2, you have to make a shift. So that will be minus t minus 2. And then the heavy side for this one here will be e to the minus t minus 2 minus t minus 2. Right? So that is how you'll get your result here. So I want you to take a look at it carefully, right? This is some of the things that we will be focusing on for the next, for your midterm, right? Finding the derivatives of the differential equations using the Laplace and the Laplace inverse, applying the Heaviside step function and so on, right? And some of the things we did earlier as well. So I will update you as we go along. Right, just one thing again to mention that right, hopefully I'll be able to access the my e-learning by today. So anything that is important, I will put it into there so you could access it, right? And so I want you to focus on all these things that we did so far, right? So I think up to about page 67 is what we'll be focusing on for your first exam, which is your midterm, right? Next day I will go through more of the questions on the in the finance text, right? Some of them I've written them out. So I'll focus more on the problems next day, maybe a little on the theory, and we'll continue. I'll update you as things progress, right? So any questions? Okay, so if you don't have any questions, then we'll end for today, right? And we'll continue again on Friday, right? So take care. See you on Friday at 1.